Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In this video, we're going to revise a little bit the variance formula for the beta 1 hat, and there is a very important reason for it. The formula that I introduced previously about the variance of the beta 1 hat was that sigma squared divided by the spread of the x, or the variance of the x. However, I would like you to remember that this formula is mainly for the simple regression. Once we move on into multiple regressions, this formula is changed to the following. And we have this new element that is being added. And we're going to talk in this video, why does that need to be added? And what is its role? And what is the intuition behind having to add this new term when we move on to multiple regressions? Okay. So, a quick reminder, the sigma square that we saw here was the noise level, sigma square, and then we've got here the spread of the x. The key takeaway from the list of key takeaways was that more variation we have in x, it means we will have more precision. Okay? So what happens, or what changes the moment that we actually add more regressors into our regression? So imagine now we have y equal to beta null plus beta 1 x1 plus beta 2 x2, and we can continue like this until some beta k xk plus an error term. So in here, something needs to account for it. Basically, the fact that we have all of these new variables. And it seems like the only connection at a first glance that we can get for this new term in here to the fact that we have a multiple regression, it's exactly adding more variables to the regression. The 1 minus rj squared, it's sort of a penalty that is being added because we are dealing with multiple regressors. Now, where is the r squared j coming from? And what does it mean for us? So the r squared, for those of you who have worked with econometrics longer, you will already know that this is a measure of fit for OLS regressions. And if you don't know that, don't worry, because we'll cover the r square in more detail in another video. But for now, just remember r square is a measure of fit for the OLS, and in a sense is telling us how good of a model you have come up to explain the variation of y given the x variables that you have included in your model. Now, the thing is that usually if whatever xj is uncorrelated, so any of these x variables that you have put in here, if xj is uncorrelated with any of the other regressors that are also part of the model, then rj squared is actually going to be 0 because it's a reflection of the fact that there's not any way, for instance, this x1 is correlated with x2 or any of the other x's that you have in here, okay? If that is the case, meaning no correlation whatsoever between xj and all of the other x's, then we'll have that 1 minus rj squared is actually only equal to 1. So in a sense, what you're doing in here, this entire expression is going to be equal to 1. You are dividing by 1. So in a sense, you don't have a penalty per se when xj is uncorrelated to any of the other regressors. However, what if we've got, let's say, x1 highly correlated with another of the regressors, let's say x2? what that means, based on the definition that we have of R square, is that if I had a regression that goes x1 is equal to alpha 0 plus alpha 1 x2 plus some error term v. So if I were to run this regression, I would get a measure R square out of this regression, which connects me my x1 variable to the x2 variable. Okay? Now, because whenever I have so many like variables in my regression, I can't go and write R12 or R23, any combination of two variables that are correlated with each other. So most of the times the reason why we use Rj is to indicate, well, I'm taking the R square measure out of a regression that I would get out of picking whichever J variable I have on all of the other variables included in my original model, where the Y was the dependent variable. Okay, so in here, this J will coincide to whichever X you have now chosen to put on the Y place. Okay, so it's not coming from the regression. And this is a very important thing to remember. This R squared J is not coming from your y regression on all of the x's, so beta 1 plus beta 1x and so on, okay? But it's coming from this kind of regression. Now, if x1 is highly correlated with x2 in this regression, it's going to mean that this r square 1 in this case, it's very close to 1, okay? Which means that your 1 minus rj square is actually going to be very close to 0. So it's going to be a very small number. Okay? Now, what happens when 1 minus rj squared becomes a very small number, knowing that it's in the denominator of the variance of the beta 1 hat? That will mean that the variance of the beta 1 hat actually is going to blow up or explode. Okay, as 1 minus rj squared is very small, which means that the entire denominator here is very small. So you have some sigma square, which is being divided by a very small number. The variance is going to explode or blow up. Okay, this is the mathematical expression as well for multicollinearity. And this is also the reason why we don't like multicollinearity, because when regressors overlap in information, the precision of the coefficients basically collapses. And let me write that down because it's very important, of a key takeaway for you. So when regressors overlap in information, the precision of coefficients collapses, okay? And in a sense, it becomes very difficult for you to actually, in a sense, find out what is the true effect of one beta versus the other beta, because these x1 and x2 now are so closely intertwined, okay? Why does this matter? Well, keep in mind, this formula was very important for us to talk about the precision of our estimation on the beta 1 hat, okay? So this formula is also teaching us, does adding regressors increase the variance of the coefficients, even if they are relevant? And the answer is yes, okay? So this formula does teach us, and keep in mind, this is going to be a very important key takeaway when we get a little bit more in deep into what does the R squared do for us. So I'm just gonna put an exclamation mark here, that adding regressors can increase variance of beta 1 hat, okay, of the coefficients, even if they are irrelevant. Okay. The next key takeaway, highly correlated regressors means we're going to have imprecise estimates. Now, if you are wondering, well, what about the matrix formula for this variance? Keep in mind, I mentioned that when we do the variance of beta hat for the matrix formula, we don't add here 1, 2, or 3 because we're literally estimating the entire vector of the betas. So we're doing the same thing for the variance of the betas. It's still going to be sigma square x prime x minus 1 because this 1 minus our j square element is actually hidden in the diagonal. And you don't need to worry about what the diagonal is right now, but just keep in mind nothing is going to change representation-wise for the matrix notation, but it does change for the scalar notation. And these two conclusions in here are part of the reason why we have to include that term in here. So in a sense, this 1 minus r squared j, you can think of it as capturing the strength of multicollinearity. I hope this video has managed to give you a bit of an insight of why we have to change our variance of beta 1 formula when we move from the simple regression to the multiple regression. This is a formula that comes up quite often in examinations because of the many repercussions and for the many intuitive key takeaways that it gives us. So make sure you remember this formula as well, and make sure you understand the dynamics and the intuition behind every single element that is added into them. And I will see you in another video.